From the last lecture, you have any question? Any queries, questions, comments, anything? No. And I understand that you had a hands conversation on X-ray astronomy yesterday. And how was it? Okay, so you could can relate some of the content of my lecture to the data analysis. Okay, all right. So I was discussing yesterday that the X-ray observations essentially produce the so-called image list, and these image lists have several attributes, and the most important attributes which are relevant for science are the arrival time of photons, and from the arrival time of photons, one can generate a light. I think you already generated a light from the event list. Is that correct? How did you do that?
On a good time interval.
Yes. So you have to use intervals which are scientifically accepted, the so-called good time intervals. So what you do is, I'll come to that. But given the list of photons with the arrival times in the detector, you can use this information to generate a light curve or time series, which is nothing but the flux or the count rate is a function of time. So how does the source is varying in its emission output? That's the light curve. And when you have the other attributes of the photon are the X1 position in the detector, which tells about the arrival direction. For example, if I have a telescope and a two-way detector, if the photon is arriving from this direction, then the photon will fall in some pixel here. But if it is arriving from this direction, it will fall in another place. So the positions in the detector are actually telling us about the arrival direction, and using the XY positions of these photons or events, one can generate the images, which we also see. The third important thing is, of course, the energy information, which is contained in this residual called pulse height amplitude or the pulse invariant, which we have discussed earlier. And one can use this information to derive a spectrum, which we call count spectrum, which essentially tells us that the number of counts is a function of this pulse height activity or the pulse invariant. And that's the basic product you have, and then from there you start analyzing the data and then you can derive science. So first look at the light dimension. One can use the arrival times of the photons in the good time intervals and derive the light. So what one is doing, one has this arrival time sequence of times. Okay, first photon at the 0.5 second, another photon 0.6 second, like that. It goes on. Then you can count the number of photons in a fixed interval. Let's say in 1 second interval. In the first 1 second, I have 15 photons. In another 1 second interval, I have 20 photons, and keep on plotting that. And of course, you can then divide. Okay, you have a mean time of 1 second. Then you can divide with that and calculate the instead of counts, it's count rate. So that you are plotting is a function of time. This is what is doing. Use a light curve. It's very simple. You have the list of the list of arrival times, and you are making a histogram out of that analysis. And that gives you the light curve or the time series, and it tells us how the count rate number of photons arriving at our detector from a particular source is changing as a function of time. Okay, so if you have, I mean, most of the stars can also be variable, but a large number of stars are steady in their light output. So there is, you will not see variability. But in X-ray sources, particularly in high energy the sources can be really highly variable. For example, this one is a source called VX9 minus 2 is an X-ray binary. And if you look at the count rate, it is taking from about close to 1 and then going up to 6 or 7. And in a very short, you see that it's 800 seconds, 1000 seconds, 1200 seconds. So it's a rapidly going up and down, going up and down, going up. Okay, so these kind of variability are very, very interesting, and this is by what we call it the X-ray timing. This is an area of X-ray astronomy. Is essentially study of the the variation of the X-ray emission as a function of time, and then trying to investigate what kind of process or what kind of changes is happening, is occurring in the source, which is producing this kind of or any other kind of light. And there are sophisticated timing analysis tools. For example, one can use Fourier transform, derived power spectrum, and look at whether there is a periodicity, etc. So there are lots of techniques you may have been told about few of those things. But this is where, from the observations you derive the light cut, then you start analyzing the data in order to understand the nature of that X-ray source or the astrophysics of that particular source. And as I mentioned yesterday, this X-rays are producing constant violent processes. So almost all finite X-ray sources are variable, and some are in fact extremely variable, which means monitoring the source, monitoring an X-ray source at a function of time, gives a lot of physics information about the nature of the source. It is not like another area. For example, as I was mentioning, if you're looking at a galaxy, for example, normal galaxy, or most of the stars which are not variable, you have one observation that is the information available. They are not variable in fact. But high resolution sources can be highly variable. Therefore, the observing as a function of time of monitoring. Maybe today one observation, tomorrow one observation, or throughout the day observation, or even monitoring for weeks and a couple of weeks, and then looking at the variability. So that gives some very important information about the nature of the source, and the timing is basically these variables. So what are the questions one can ask observationally once we have the light curve of time series resulted? So first, even simple things like that's the X-ray flux variable time, yes or no, that also already tells something about the nature of the source. What is the time scale of variability? Whether, let's say, the light output, the X-ray flux is changing by a factor of 2 in 100 seconds, or half a day, or 1 week. These are very important information. The variability time scale on which the source flux is changing significantly. These are very important physics information that helps and understand, because when we talk about the physics of the source, what kind of processes, what kind of sizes, what kind of geometries can actually give rise to variability over certain period of time scale. So that relating this observed quantity variability time scale with the physical process, what can give rise? These are the important things to probe in X-ray sound. Whether the variability is periodic or aperiodic. For example, in some of the binary systems, when stars are going around each other, there can be periodic signals or pulsars, of course, if the pulses are periodic. So that also tells us about the nature of the source and, of course, what is the period and all that. The variability amplitude, but what is the factor with which the flux is changing, whether it is factor of 2 or factor of 10 or factor of 100. So for example, in gamma ray burst, if you have been told, so there in gamma ray burst, the gamma ray emission can change by a factor of 100, but very quickly, or even more than that. Because there was before the burst, before the gamma ray burst, there was nothing, but when the burst is there in very short time scale, starting from fraction of a second to all the way to 200 seconds, depending on the type of gamma ray burst, and the flux can suddenly shoot down and then come down very quickly. So then this becomes very interesting, because of this kind of nature, here this becomes very interesting as well. Then, of course, there's something called fractional variability amplitude or fractional RNS, which is a measure of variability. I'm not going into the details, but the amount of variability you measure is number, the fractional root mean square. The variability. What you do, if you have a time series, you can always find out the mean, and then the root mean square, you can find that out. And once you have the root mean square divided by the found fit, that becomes the fractional RNS. If this root mean square is high, then the variability is high. If it is low, then the variability is low. For a constant source, which is not varying, the RNS will be 0, of course. Then once you have the light curve, one can derive the use of Fourier transform techniques, derive power spectrum density, then look at what is the shape of this power spectrum, whether there are narrow peaks in the power spectrum. If there are narrow peaks, those peaks actually tell us the periodic nature of the source. There may be peaks, but they are not exactly narrow. There is some kind of width. Then those sources are costly. periodic, not perfect periodic, but the period is changing in some time, in some fashion. So if there are other features like what is the shape, it is the power law, what is the index, and whether there are breaks in the power spectrum. So all these are very important information one derives from the light curve. Any then of course any variation of the parameter, for example, the period is changing, or the fractional RMS is changing, or the power spectral density is changing. If you have possibly any oscillations, this peak with some width, whether that is changing. So all this kind of thing it will give us very important information. Then using the timing observations, one can also study the variability and the energy spectrum. How does the energy spectrum is changing? So that tells us about the physical process, how changing. For example, let's say there are particles being constantly accelerated, or there is a sudden acceleration of particles that will that will change the emission from the region, and therefore then the energy spectrum of the source as well. And if there are any correlated at other wavelengths, for example, many of the sources are emitting over many different bands. For example, optical, ultraviolet, X-rays, gamma rays. How the source is changing at different wavelengths, and how these things are actually related. How the change at different wavelengths are actually related. What is the kind of correlation? Whether if X-ray is going up, whether the UV is also going up or is going down. So these kind of information all become important. Okay, so yes.
But what is the reason behind the variability? Why is it always
So there are variability itself is a very rich field. There can be very different regions for variability. For example, pulsar. Pulsar, of course, is a magnetized neutron star. And in this case, you are observing the radiation from the poles. Right? And then if the magnetic axis and the rotation axis are not the same extent, there is some interaction between the magnetic axis and the rotation axis. And because the axis is rotating and they are observing the radiation of the poles, then periodic, very regular periodic variations you see because of this rotation. In different classes of objects where some of the speculating objects like the black holes which are accreting material or neutron stars which are accreting material, the light output also depends on the accretion rate naturally. So that accretion rate is if it is changing, then obviously it will change. Even if there is the accretion rate is constant, there are a lot of changes in the innermost region where things are not stable. Things are pretty dynamical. There is some kind of outflows, there are some kind of winds, etc. And sometimes the inner accretion risk may disappear because it is thrown out as in the form of outflow. I mean, there are so many complex physics involved, not just one type of thing. And that's the subject. I mean, in research, that's what a lot of people actually study these things.
one more thing? Can we predict the source by studying the way the pattern?
If it is a periodic source, then obviously you can predict, okay, it is going changing in a periodic fashion. Then after 2 days or after 3 days, what will be the flux you can predict. But many of these accreting objects in the high energy systems are aperiodic. I mean, if you derive a power spectrum, it's more like a power lamp without a clear peak. So no periodic. And that kind of very aperiodic. And once you have such things, you cannot really predict what is going to be flux tomorrow or the day after. Okay, so the next thing I want to discuss is this imaging in X-rays. As I mentioned, one can derive the image. So one can derive the images again from the event list, but this time using the arrival directions, which are in the form of this XY positions. So now one earlier we've been in time and derived the light curve. Now we've been in this X and Y positions. So for example, we have this, let's say the positions in X-axis 0, 1, 2, 3, 4, 5 like this. The Y-axis like this. Then we can count, okay, between 0 and 1 in X-axis and 0 and Y-axis, how many photons are there? And then you keep doing this for different coordinates, different positions, and then put the number of terms in each of those coordinates, those pixels you can see, and then you have the image. So this image essentially is the distribution of this X-ray emission over the spatial dimension and X and Y direction. So and looking at the morphology of the source also gives us a lot of information about what kind of what is the nature of the source or what is the kind of this. For example, here we have this diffuse emission, which is either extended or diffuse emission, in addition to these particles. Okay, and diffuse emission, first of all, it is coming from spatially extended region, and this is obviously well resolved. You can even measure the size of this entire thing, whether it is a kiloparsec scale, whether it's a megaparsec scale. And for example, if you are observing a galaxy, whether this emission is coming from the central region or from the entire galaxy, and how it is varying within the galaxy. So this is also whether it's in the central region, it is brighter, and when you go outside, it is decreasing. All this kind of important information. And then once you have the diffuse emission, then some of the processes will be the diffuse emission will generally be, there will not be variable on short time scale. So then if the diffuse emission you can directly relate with particularly with the hot gas, thermal emission. While the point sources, which are X-ray binaries, can have completely different origin for their X-rays. And there are certain, this is what I was saying, diffuse emission gives an intuition about the morphology of the source, and different kind of sources will have different morphology. For example, this one is the Crab Nebula, and here you will see this is the position of the neutron star, which is rotating very fast, and this is the jet here. And then there are these ring-like structures that are this kind of, and this connects to the larger structure. So then you study the process. What kind of process is there? Neutrons are rotating. There are jets coming out of this thing. What is the process is happening and the jet? So all that kind of thing, the morphology, spatial distribution of the emission, then the structures within that, like the jets, wings, etc. Then you have to come up with a physical picture how this entire thing is being produced, and all these structures as well as any kind of time variability, all the energy spectrum, everything has to be explained, and all of this information helps in doing that. These are some of the supernova remnants. Again, with the hot gas as well as because of the supernova remnants, the particles are being accelerated in shocks. Those will also emit, so there will be some Bremsstrahlung and thermal emission, as well as non-thermal, some non-thermal emission. So you have spatially extended region. Then you can also choose, okay, what is the spectrum in this part, or what is the spectrum in that this part. Maybe the different parts of the spatial regions have different kind of processes. One process will be dominating in one region, another process is dominating in another region. So there are lots of possibilities. So having this information and then closely analyzing the data, connecting with physics, that's the what. Okay, so the last thing I want to discuss is X-ray spectroscopy. As I mentioned, one can derive the spectrum from if you have the energy information of the photons, and the of the photons content in this thing called the pulse height amplitude or the pulse speed rate. And that is represented as a channel number, detector channel number. So the detector channel number is a measure, in a way, it is a measure of the energy of the photons. So the detector channel number is nothing but what I said earlier, the pulse height amplitude or the pulse. Now let's say one particular detector may have some 1,000 channels. Okay, so it's starting from 1,000 or something like that, and each of these channels will represent some energy. So if that is the thing, then what you do, you count the number of events in one event channel, and count this as the T data as a function of I, as a number of events as a function of this channel. And this is essentially the plot this basically count spectrum. This is not physically invisible, but it is only thing is that we are counting the number of photons which have been detected our detector and then plotting either function of the detector channel, which we are saying it's the channels are measure of the energy. But obviously, when there are lots of photons coming, so then all the photons do not get detected. There are all sorts of instrument complexities. Okay, some energy, more number of photons will be detected, and other energy, lesser number of photons will be detected because of the efficiency of the detector. The instrument is a function of energy. At some energy, the X-ray optics cannot be reflecting that well. At other energies, the X-ray optics may itself be reflecting well. So there are quite a bit of complexity involved, and it's not easy to derive the spectrum or the source spectrum in physical units. Where when we say the source spectrum in physical units, it's like think of the black body spectrum, for example. You have the flux density as a function of the frequency or energy. And when we say flux density, that's in energy units of per centimeter square per second per hertz or per unit energy like that. And then I just plotted the function of the sphere energy. That's the spectrum, the physical spectrum which we're talking about. What we get from the detectors is the count spectrum, number of counts is a function of energy. So going from count spectrum to the flux spectrum is not an easy process because the instrument modified the spectrum in a complicated way. And different instrument modify the optical spectrum in different ways. So understanding the instruments, how the instrument performance, how the instrument responds to X-rays, that's a very, very crucial. If you do not have a very good understanding how the instrument responds to X-rays, then we may infer incorrect source spectrum. That is why in X-ray astronomy, knowing the instrument knowing the instrument response is very, very crucial. This I saw in let's say the real spectrum of the source is the flux as a function of energy. That is what is emitted from the source. Okay, and that particular spectrum that the source is being observed by the instrument. So then what we are getting is this data number of counts in the different channels. And obviously, when you look at this equation, this flux spectrum, which is our physical spectrum, that is completely getting modified by these quantities. And these quantities essentially contain the instrument response, how the instrument is responding to the X-ray spectrum. And we will talk about it more on this. So as I mentioned, this DI is the observed number of counts in any digital channel I. Okay, and it contains source plus background. So if you have a source spectrum like this, that will get modified and then result in the source count, the number of counts emitted by the source. But then there is a background because when we are operating with any detector, you can just let's say it's like a star or any kind of fine source. Our detector will always observe that fine source and the surrounding background. So background is always there. You cannot just observe the source alone. Whenever you make observation, source plus background will always be there. That is why background is innate. So, and as I mentioned, this quantity RIE multiplied by this AE, this is the instrument response. This is how this instrument response is how it is modifying this flux spectrum and giving rise to the count spectrum in our detector. Okay. So then I said it's an instrument response, but what exactly is this? So let's look into this. So according to this equation, all the source physics is contained here in the F is a function of E, flux is a function of energy. That's the physical spectrum. So if you all our astrophysics is there. I mean the spectral spectroscopy, the actually astrophysics is here. And all the instrument physics is in this instrument response. So if our aim is to understand the spectrum of the source, which requires a very good understanding of the instrument physics, which in the instrument response. Okay, what it is not only instrument response, but the background. If we have an imaging detector, then we are measuring the background simultaneously. So we have a very good handle on the background. But if you are using a non-imaging detector, particularly the kind of detector I mentioned, a detector, proportional counter with a collimator. So then we are just count from a certain region of the sky, and we don't have the imaging information. So our background and the source counts are completely mixed, and we have no independent way of measuring background. So in such cases, this background is considerable uncertainty as well. And people model, and for such detectors that model backgrounds, and so of course based on, like I say, observations, etc. So, but the main thing here is that instrument response. Let's try to look at this instrument response. So this is the product I mentioned to you, RIE, and the product is also called the response matrix. And this quantity RI is called the distribution matrix, and I will tell you what it is. And this A is a function of energy, is the effective area as a function of energy. And when we say effective area, so imagine we are using a telescope, optics, and it has certain collecting. Okay, it may be then 1,000 centimeters square or 500 centimeters square. That is our collecting area. And when you have a geometric area of your telescope, then there will be some holes, some structures which are blocking all these things. You subtract for all those things which are not contributing to the collection of photons. That's the net collecting area. Okay. But when these photons are collected and reflected, and let's say in between there are filters or some other structures through which these X-rays have to pass through. So then it has certain transmission efficiency. So that transmission efficiency is multiplied by the collecting area. And now after passing through whatever structure is there, they reach to the detector. And the detector will not detect all photons at a given energy. It may detect 90%, 95%, 70%, 80%. And this fraction again changes with energy. So this, in technical terms, these detectors have certain quantum efficiency. And this quantum efficiency essentially tells us what fraction of these incident photons are actually detected by the detector. And this fraction changes varies as a function of energy. So therefore, this quantum efficiency, if it is 100% detection, then it is 1. If it is 50% detection, let's say 0.5. So this quantum efficiency is also multiplied to the collecting area or any transmission efficiency and the detector quantum efficiency. So the product of all these things, whichever affect the detection of photons or the collection of photons, etc., is called the effective area. And here is some of the examples of the effective area. It's a function of energy. So you see, there are some of the soft picture. I mean, if it were just a mirror and it's reflecting everything with no energy dependence, it will be flat. Okay, but because there are a lot of energy dependence and the way X-rays interact with your collecting telescope or the filter transmission filter, etc., or the detector, etc., that is why there are so many of these features. And these features, if you may come across, these are called edges, absorption edges. And this is the various elements present in our telescope and filter and the detector support structures, etc. Because there's certain energies which are selling either K cell ionization energy or other cell ionization energy, where the photons are differentially absorbed. Absorbed means they are removed from the detection by the structure, not by the detection. So therefore, the collecting area reduces those particular energies. This is what is happening. And this particular state, yesterday I mentioned this absorption cross section, which varies in 10 to the power minus 3. It is a result of that. This particular state is absorption is, and this change in X-ray. Another absorption is, another absorption is. So this is the elements. For example, if you have let's say you have an X-ray beam and you have a filter, and a thin filter something, and then X-rays have to pass through this. This filter, then you have to look at what are the constituent atoms of this filter. Maybe it has carbon, oxygen, or nitrogen. Then this carbon, oxygen, nitrogen absorb preferentially at the K cell ionization energy. So therefore, at the K cell ionization energy, the transmission will change. Those photons will not be transmitted, and those will be absorbed. Like that, these things change, and with laboratory, with experiments or even theoretical modeling, these things are actually determined. Very unique. How many atoms are there in this structure? What is the density, etc. All these things come into this, and even calibrating these instruments, laboratory calibration, or even offshore launch, these are extremely involved work, and technical. This requires technical expertise as well. And that is why, and then making it stress qualified, of course, is very, very challenging. So the entire area of X-ray, developing X-ray telescope, calibrating these things, even also observing from space, all these things are really challenging and very exciting as well. Okay, so that's about the effectivity. The other thing that is RIE. This is the redistribution matrix, which is a function of the energy channel I and the energy of the photons itself. So this is called the instrument response. Okay, this somewhat. Anyway, so this RIE is called the redistribution matrix, and this is a function of the energy channels as well as the energy. Now you imagine a monochromatic source. Monochromatic source means there's a source, an imaginary source, basically it is single energy. Okay, imagine it 6 kV. And we have a detector with all this channel information, detector channels, some thousand channels, something like that. Now there is one photon, all photons have single energy, and these photons are interacting with our detector. So ideally, if this detector were ideal detector, then all those photons at the same energy would fall at the same channel. But this doesn't happen. What really happens is that, for example, in this particular case, I think it was some photons from 6 kV. Those photons are being detected at all different channels, not just single channel. I mean, if it were all the photons were detected at this channel only, then there will be a delta function, just one line. And then, okay, these photons then will quickly convert, okay, this is the channel and this is the energy, and you have a spectrum, no complexity. But because of this thing, photons of single energy are getting distributed over a large number of channels with complicated distribution. This makes the life of X-ray astronomers very complex, and this makes X-ray spectroscopy very difficult. And this is the response of the instrument to a monochromatic source. Okay, and this kind of computer response is due to the fact, due to the way the X-rays interact with the detector material. So what really happens? I mean, let's say these photons are absorbed photoelectrically, and then of course there is the electron of these photons. The entire energy of the photon is converted into the signals or the electrons. And if all those charges are actually collected, then we have the photon detected in structure chain. But for some reason, some amount of charge is lost. So then we are then the photon which is detected will fall in a channel which will correspond to the lower energy. Okay, and because of the atomic structure, you have some of these features. For example, if a photon is absorbed photoelectrically, then let's say the case electron is ejected out, then another L cell photon will jump into it, and that will produce a K alpha photon. Now this is an X-ray photon. I think this photon can actually escape the medium, escape the detector. Then equivalent energy of that thing is being lost. So whatever is the initial energy of the photon, initial photon, and that the K alpha photon energy must be subtracted, and then whatever is the energy divided correspondingly, that comes at the escape peak. Okay, that's the escape peak, the L escape peak, like that it will come in a series of this. And then there is a low energy tell particularly like this, because you need to exclude these things, there are these low energy, which essentially tells us that because of some reason, because of in the detector, we are not able to collect all the charges produced by the photons. Charges are somehow lost. Therefore, that is why no electrical are there. And determining this saying, including all these peaks, say the peaks, heights, etc., widths, etc., etc., and this more detail in the laboratory characteristics. Not even after launch, we can think change also. So if you have made some mistake here, then final science or final assessment is may not be done. So that one of the one aspects convenient. So this is the redistribution matrix. Essentially, photon, how the instrument is distributing photons of some energy over different channels. That is what is deciding the redistribution matrix. It is also it also is the probability that a photon of energy E will be detected in a channel R. So if you integrate over the entire all the channels, then it should be the probability is 1 because the photon has to fall somewhere in some channel. Okay, so if you compare this thing, this redistribution matrix, redistribution function, what we have in astronomy, with that in optical ultraviolet or optical astronomy. You know how to do spectroscopy in optical, or even in the labs. Do you know? Or have you done any kind of experiment in the lab? Any light, anything? Or what have you done? Have you done anything? Taken a spectrum of anything? Sorry? Hydrogen. So what do you do? Yes. So roughly you have a light source, you put a prism or a grating, then that this is a dispersive element, that disperses the light in, and this is over where along the dispersion axis, which is a measure of the distance along the dispersion axis, no problem. So you are separating like that. But if you have a source, it is single wavelength. Let's say at the H6563 angstrom, SF per wavelength, nothing else. What would be the spectrum? Let's say if you're using a grating or you can have prism. Will you get a single line? The line will have some width. Huh? It will have some width for various reasons. Even in quantum mechanics, there is a reason why there should be a width. Because when there are transitions, these steps have some lifetime. That results in the width, natural line width, so-called natural line width. And if your light source has gas, which are because of the temperature, they are moving in the here and there. So some of the elements, some of the atoms will move towards us, some will away from us because the Doppler shift this will also be good. But all of these things, even if there is a instrument resolution, the current quality of the instrument, even whether it is that only broadens the line little. Does not make like what we have in X-rays. So if you have a spectrum, if you have a source emitting at only one wavelength, then you will get a line, but that line will be slightly broader. It might look like a Gaussian function with a narrow. That is what happens. And in X-rays, they said this is not simple. Here you can probably approximate the Gaussian, but there are lots of other things. In optical astronomy, you get a narrow peak here with a Gaussian, roughly speaking. And in X-ray astronomy, this becomes a much more common. That is the difference between the redistribution matrix in X-rays and what we would expect in optical or ultraviolet spectroscopy. I already have explained what is the effective area. So in X-ray astronomy, most of the X-ray spectra are of moderate resolution, unless you have an X-ray grating. Then that you can actually acquire high resolution. So for example, the moderate resolution spectra are excellent. You can control CCDs. Okay. So and another important thing in X-ray astronomy compared to optical array is that here the continuum is also very important in addition to the lines. And whenever you are studying the spectrum, then you have to study both the lines and the continuum. It's not like in optical astronomy. So many times people are just interested in the lines. So they measure, okay, the continuum they'll treat like a background or something, and then just measure the line intensities look at the line parameters and then derive the fix. Here it is the continuum, which is I would even say this continuum is more important than the line, particularly analysis, which is when you are trying to speed non-thermal astrophysics. Thermal plasma gives rise to the lines, but non-thermal processes give rise to continuum. Therefore, the continuum becomes very important. So you have to study both the continuum and the lines together, not separately. Okay, so another important, we have discussed the kind of data, the instrument, the metric, the area, the source spectrum. Another uncertainty becomes significant, the background. The background, the number of backgrounds from the background are detected in different schemes. So where does this background arise? So the background has different, source of the background could be different things. First of all, in every direction in the sky, there is so-called cosmic X-ray background. You look at any direction, you will get some X-ray emission. You may not see any source, but there will always be some X-rays. This is due to cosmic X-ray background, and this is people have done lots of work, and it turns out that it could be due to large number of objects very, very far away, particularly some of the active galaxies. This is cosmic X-rays. So whenever you are pointing your telescope to observe some source, like Crab Nebula or something, in addition to that, the Crab Nebula X-rays from the Crab Nebula, there are also observed the cosmic X-ray. That is one source of background, and which people have measured, and even your build-out view, the T-area, etc., you can predict how many photons this cosmic X-ray background actually will contribute to your in your observation. The other things which are more complicated are so-called internal background to the detector. So what really happens? So in this case, the background is produced by charged particles, usually protons and electrons, and because the satellite is orbiting near a space environment, and there are lots of charged particles which generally interact with the detector. Okay, and then again, these charged particles can generate signals, especially the electrons they can generate, and which can be confused with X-ray. So that is the source, one source of the background. For example, if this is the South Atlantic anomaly. This is the region above something like 500 kilometers above Earth's surface. So this region, the so-called South Atlantic anomaly, has a high concentration of dark particles. Okay, whenever the satellite passes through, they have to they interact with lots of these dark particles. In fact, many of the satellites and their instruments switch off when they are passing through the South Atlantic anomaly to save from, because otherwise they can be high voltage, and then the charged particles interacting with these things can destroy the entire thing as well. So many of the satellites, many of the things actually switch off, but because the high concentration of charged particles, X-ray can generate from the background. So the background comes within.
Is that only an interference in X-ray or other ways?
See, in X-ray detectors will generate lots of signals, but in other satellites, even if there are no detectors, that will cause additional problems. Even that will cause additional problems. I mean, whenever you have there are other effects also. For example, when you have charged particles affecting with, for example, semiconductor detectors, which are actually kind of crystals. So they will cause impurity in that those detectors also. They will remove some crystal lattice, and they will remove some of these atoms, and then change the crystal structure. Therefore, performance of it will go down. There can be micro meteorite. When that can badly destroy the electronics of processing electronics of the instrument, and if there is a very high voltage available, charged particles can cause short circuit and things like that. So there are various effects, and depending on the instrument, the type of instrument, what is built in. So many of them will also switch up.
So what this cosmic X-ray background that we're talking about, what is the source of?
The cosmic X-ray background, as I mentioned, in any direction if you look at, there are some X-rays in this. We cannot pinpoint the source, but when people study these things, they can the spectrum of the cosmic X-ray background resembles with the spectrum of a large number. When you combine the spectrum at various very different distances, there are type 2 agents, so-called complex agents. Okay, if you combine, then you get a spectrum which resembles to this cosmic X-ray background. So people think that the cosmic X-ray background is contributed by discrete sources at very different distances, and most of these different distant sources are agents, complex agents. Okay, of course, the activity within an instrument, even if you try to ensure, there can be trace amount of radioactive elements in the instrument or the reactor itself. If there is a radioactive element, then the radioactive element may be producing beta particles or gamma rays or whatever. So that can also produce background. And not only that, in space when these instruments are operating, because of some proton interacting with some nucleus or something, that we can even generate the radioactive elements there also, and they start producing some signal. So that will work like background. And in the field of view, if you are not able to distinguish different sources, you are observing a very bright source, but then in the field of view there will be other spectral sources, and in that case, that those will also contribute to background. Okay, so once we have the background, once we know the instrument response, the matrix, the area, etc., then how do we infer this? The flux spectrum. This is the ultimate aim of X-ray spectroscopy. Then obviously, naturally, you will try to solve this. So you can write this in a matrix form, or you can because you can discretize this channel. The channel numbers are discrete number 1, 2, 3, 4, like this, not continuous. You can also define energy bins in a discrete fashion, and then write a equation in a matrix form like this. And then you may think, so now to find out this quantity Fj. Now this is Fj, the flux, the energy flux in different channels. Then to do that, you may solve like this, to get the inverse of this matrix and do that. But this kind of thing doesn't work. People can form this mathematically. This is really a problem to invert this thing. And if you first of all, this matrix is non-diagonal, because when will you get a diagonal response matrix? Can you think of it? So you will get a diagonal response matrix if a photon of a given energy always falls in a given channel. But we do not touch photons at the same energy can be detected in different channels. Once you are detecting photons in different photons of same energy channels, you go to that response matrix, no longer in its diagonal. And then find the inverse of that matrix is many times it is not equal. Okay, and even if you are able to do in some simpler cases, then because we have this points, whenever we are measuring this photon number of counts, there is a Poisson noise. And even if you try to find a solution and then change just into the photon noise. For example, if you have something like 25 counts in a channel, then just into the Poisson noise, there is a consistent of plus minus 5. Okay. So if you have obtained a solution for 25 counts, say in some channel, and it changes to 25 to 24, okay, Poisson noise can cause that. The solution becomes unstable. That has been shown by a lot of people. So this directly converts this. First of all, this matrix is a large matrix, because as I said, the channels can be 1,000 or even 1,000 sometimes more than that. So 1,000 by 1,000 matrix becomes very much a problem. So because of this difficulty, what people do, what people follow is a completely different way. So here, of course, you first write in the matrix form, and what you have is this counts. This is how you have subtracted this background from the detector, and then you are getting this count C in different channels, which were with the discrete form. We are writing C, let's say C I, the number of counts in channel I. This is the information we have from our observations. Okay. And in other, what then you do, and we also have the instrument response provided to us by the instrument. Okay. Then, because we cannot decode this thing, what we do, we assume certain form of this thing. It could be, let's say, a very simple power law or a black body or anything like that. Or based on our past experience, past research, what would be the most probable spectrum, we guess that. And then, once we have the spectrum, then we can calculate this entire form. Okay, then we will come up, and now this is our model spectrum. So therefore, after calculating this thing, what we have is a model count. And then we compare our model count with the output count using some statistics. If it matches very well with our model count with this choice of our model with certain number of parameters, if it would match with this output count, then we say, then we statistically quantify, okay, our model is acceptable or model is not acceptable. Like that, we can make the next step. This is what we do in this process, what is called forward fitting method. We define a model. That model, as I said, could be a power law. Power law has two parameters: the normalization of the power law, the index of the power law. Like it can have a black body capture is one parameter. The black body flux or the normalization that will be another parameter. Like you can have synchronism or whatever physical processes you have, you can also derive a spectrum with certain parameters. Okay, those parameters will be specific from source to source. And once they define the model and then calculate this model and multiply with the detector response. Once you multiply with this detector response, R is it. And then whatever you have, this model counts you compare with the data using something, and if it is not, if the comparison is not good, if the model counts do not match with the output counts, you change the model parameters or change the models and do this follow do until you get a satisfactory until your model describes the data satisfactorily. And that of course what uses statistics, etc., which are not going into the details. But that is how this process itself works. And once you have explained this of the model, then you have the source model, which will be like a physical model, which will be the flux, energy flux is a function of energy or zero. Then you can infer whether it is a black body or this is coming from an accretion disk or it is coming to it is just a proton kind of emission from a jet or something like that. So then from there you really start doing astrophysics and thinking about the more physics part. Okay, but when you are doing this forward fitting thing, because you are actually thinking which model. So that question already is related to the physics. Or what kind of source, what kind of physical processes, what kind of models. And then in the one hand you are thinking what kind of the detector, what is the instrument response, how good is the instrument response. These two things you are thinking simultaneously and trying to get a source. So that this part, unless you spend quite a bit of time, you do not get the experience enough. I mean, once you become experienced enough, I mean, in the even a power law, because the instrument response doesn't look like a power law. It can be completely different step when you are looking at the count spectrum. So by looking at the count spectrum, it is usually difficult what is the set of this. But with experience, if you have worked on observation from a particular instrument, then you can guess, okay, with the instrument, even the count spectrum, if the shape is changing like this might be like that. Or if you get a feature here, then what might be, whether it could be instrument feature or it could be the rest of the source feature, you can guess that. These things come with experience. Okay, and there are various software packages for this kind of analysis, which also allow you to give new models. If you have a new, let's say there are lots of these existing models available, and then if you have a new idea, if you want to test, you can write your own model and implement in these kind of softwares, and that's a very good work. Okay, that is how, I mean, whatever existing models are there, and you have a new rich data set, and you try all those models, and if you're not able to explain, then you have to do question. I mean, regarding the nature or the physics of the source. Then you may think of some different physical process, and then you come up with your own model, implement it, and describe it. So that's obviously the good challenge. Okay, so we have gone through the X-ray astronomy stuff, I think, sufficiently. So let me also go through briefly the different kind of X-ray sources. I have also already told you about some of the sources. Let's see. So X-ray binaries, of course, I have this case is these are binary system, and one of the components is a compact object. It could be neutron star, black hole, and white dwarf, which is emitting material from the component star, and this emission process gives rise. This process gives rise to this flow in the form of an emission disk, and that is will lead to of course conservation of the momentum of the matter will be excited. If you have any lecture on extinction or active electric nuclei or active electric nuclei, you would have come to the extinction discovery. Yes. So you are aware of this. So and this extinction process, because of the gravitational energy release is converted to radiation. That's what generates huge amount of radiation. And then very close to the black hole, because of extreme physical conditions and things are affected with PR and special energy, etc. So by studying the emission from very immediate environment of this compact object, can actually do quite a bit of complexity. Then I already mentioned the supernova remnants and the massive stars when they at their core, at their core, then after they go supernova explosions, and some of the supernova explosions end up as neutron stars. Like in this particular case, is the neutron star bomb from the supernova explosion, and it's a hot neutron star, so you see very bright emission there. And this is of course the supernova remnant. In other cases, you may not observe anything, either due to it probably produces a black hole, which you will not observe unless it is activity or unless it ends up in a binary system like that, or because of other kinds of supernova type 1A, the supernova type 1A, where when two white dwarfs merge and they detonate completely and nothing gets left out. No neutron star, no white dwarf, no black hole. You wouldn't see anything like such cases. But this brings time to study the dynamics of this remnant and the conditions, the particle accumulations, how these things and neutron stars, these kind of objects are very important in dynasty astrophysics. This is Crab nebula. This is again a supernova remnant, but it's a very different from other supernova. Here, this you know about Crab nebula and pulsar. You had any lecture or you have read about the Crab nebula and pulsar? This is one of the most famous objects in Earth. So here we have a neutron star which is rotating very fast, and it's like a particle accelerator. So it's a visualized to lots of this particle in these directions, going out lots of particles. These particles are moving in the surrounding regions and the magnetic field, and therefore they generate synchrotron radiation. Here, the central region shown in the blue is the X-ray image. X-ray image obtained by Chandra X-ray telescope, while the green one is with the Hubble Space Telescope, and the infrared emission in the red color is observed by spectroscopy. So by combining the X-ray emission from Chandra, the optical visible light Hubble Space Telescope, and infrared emission from space mission, this picture has been created. So and then this kind of things are very useful. Then you can quickly say, okay, which part is actually emitting high energy radiation, one is emitting low energy radiation, how things are connected to each other. So that kind of things are very okay, so then these are some of the examples of active galactic nuclei. This is the NGC 1365, and this is the X-ray image of this 1365, and it's a very bright nucleus embedded there with the dust and other things. You see it very bright. That's the active galactic nucleus. This is a supermassive black hole, which is material from this. This is again a combination of Chandra. This is the Chandra observation, the optical image high. Okay, this is an HSP image. This one is another example of an NTC 4590. This was the ultraviolet rays created with the astrocytes. I do not have time to talk about astrocytes, but I have already described the X-rays. I did not tell you about the ultraviolet telescope on board astrocyte. So astrocyte has ultraviolet ranging telescope, and you can acquire images in the far ultraviolet. It also has one near ultraviolet telescope, but unfortunately that is no longer functional. Otherwise, it allows produce beautiful near ultraviolet. I think this one is a near ultraviolet. And these are, of course, the observations. And the innermost regions are, of course, not dissolved. Even in X-rays, they look like this, we are in other regions are not resolved. But what we see from the study of the spectrum, X-ray spectrum, variability, ultraviolet, variability, etc. What we think is there is a massive black holes at the centers of this X-ray, which is a tricky material and forming this in this, and then in some cases there is strong jet arising from the innermost regions and launching in this direction, quite far away. The active galactic nuclei give excellent opportunity to study the regions very close to the supermassive black hole and how the jet and the disk are connected. The innermost jet could also be like the so-called hot corona, which is giving rise to X-rays through the process called complexing or quantum scattering. It was quantum scattering, which I mentioned yesterday. It's one of the process which generates broadband extra power. This is a cluster of galaxies seeing the visible light. So there is a joint galaxy, which is called the CD galaxy at the center of this galaxy cluster. Galaxy cluster, I'm sure you are aware, this is a cluster of large, it can contain large number of galaxies. If there are only two galaxies to be or something like that, this would be called groups. But then if it has 50, 100 like that, then it would be like a cluster of galaxies. So in visible light, what you see is different galaxies, the central galaxy, and then the large number of other galaxies that are part of this cluster. The same thing if you look at it X-rays, the picture is completely different. This is the X-ray image of a galaxy cluster. You do not see the individual galaxies. What you see is a diffuse emission from the cluster. So essentially, what's really happening is that medium between the cluster, the so-called intra-cluster medium. So that is filled with hot gas with multi-million degree temperature, and that hot gas is making this very diffuse and smooth kind of emission because of thermal process. Okay, so briefly let me also go to the astroset method. Many of you may have heard astroset of this. Sorry? Okay. Then you already know. Then I don't need to. If you have any question on astroset, then you can ask. You have any question on astroset instrument, functioning, results, whatever. Okay, so not about the astroset, but let me say a few things about how scientific research, particularly in the observational area, actually happens. So, at any given time, there are a number of scientific questions. For example, if I'm working on AGNs or energy then I would know, okay, these are the real science questions which we really need to solve. Okay. And how will you solve? And if things are so complex, you cannot just sit down and calculate pen and paper and solve. That is impossible. But there are so many complexity involved, so many possibilities involved. That is why computer simulations are definitely very, very useful, but cannot really solve. You need observations. So, given the set of science questions, burning questions you want to solve, then the scientists think about new instruments, the future instruments with using new technologies, and then address, okay, these questions. If you want to solve these questions, what kind of instrument, what kinds of sensitivity? So the scientists will get together, discuss these things, and then come up with a new set of instruments, and then to address those some of the questions. Okay, and then they, of course, they make the instrument, a lot of the power, etc., and it is the space astrophysics, then fly and send into the space, and then stop. And then, of course, there is a user scientific community, both in India and everywhere else. Places. Then these missions invite scientific proposals. So, for example, if I have a question or I have a science question, then which I want to address with this particular satellite. Then I formulate that question, science question, in terms of a proposal, where I will state what is the, I'll provide some kind of a background. I will also state what is the science question which I am going to address, and how do I, using this thing, how do I address this? So I will need to do some simulations, some feasibility studies. For example, I would know the what is the sensitivity of these detectors, and if I want to, let's say, for example, I want to detect the iron line, for example. So then, what is the sensitivity of this detector in the iron line band, which is around 6.4 kV? Whether the sensitivity or the collecting area of this telescope is large enough to measure the line profile very accurately, and for to measure the iron line profile accurately to my that will address my science, what kind of length of observation is required. All these things I will simulate and demonstrate. Okay, if you observe this for this much time, I will definitely get this data with this signal to noise, and then I will show, okay, that if I have this data with this signal, then I will solve this problem. This you demonstrate. So then this kind of things is actually reviewed generally by atomic agents, whether it is form satisfactory, then we will go for observations, and then the satellite mission will observe, like associate what associate does, and then data will be reviewed, then we analyze and try to solve this stuff. This is what really happens in scientific research, this kind of thing. You see this, say something like this or any other telescope in the groundless. So large number of scientists, the engineers, technicians, all of them actually get together and work to realize some of these things. And then, of course, there is a scientific community which later on use these facilities to address some of the science questions. In reality, you aim, okay, we will solve these problems, and you launch a new satellite, a new instrument. Think of solving those problems with this own problems. That's what. But of course, you solve it. I'm not exaggerating, but you solve some questions, but you also discover a lot more important questions because you are going deeper and deeper in your scientific investigations, and that obviously is the joy of science. Okay, I think I can stop here and have some questions I can ask you. Yesterday, I received okay, so people who are attending in the online mode via Zoom, they can actually ask questions, either they can type or even raise their hands. But while some people raise hand in the online mode, if you have a question, any question?
How does the background of the calculation, there's a main source behind the source that we are observing. How can we calculate the zero size?
Okay, so if you have an imaging detector, let's say once you have an imaging detector, you have an image. You have an image like something like this, and then you may have a source somewhere here, and then there are lots of this background. Okay, and you will measure the background from some region which is away from this source, and you suspect there is a source. You measure the background from different regions which are which you think is a source free. Then you also measure whatever is the amounts of flux from here and correct for the background contribution. And then of course background will have certain uncertainty, source quota, the count will have certain uncertainty. You take into account all of this thing, and then you can quantify whether you detect your source statistically in a statistically significant manner above certain sigma. But if you do not have an imaging detection, then it becomes a problem. But in that case also, people would have observed black sky earlier, not during that time. And people would have observed blank sky when the satellite is going around Earth, all along every position in the orbit, they would have measured the background because the background is not just the background from the sky, it's from the environment as well. So that is why measuring the background from different locations in the orbit, that is also important. By having such kind of measurements, people would have modeled that, okay, or even simulation codes. And now for your observation, will probably happen from point A to B in the orbit. Okay, for that point A to B, what is the expected background that will come from simulations or from earlier? So once you account for that, of course, that is less certain because this is just a simulation rather than the real options. Yeah, so there is a question by Sumed Sawan. How the reflectors for X-rays are made since they pass through almost everything. This is I think I had addressed this question. So X-rays obviously they can pass through in normal incidents, but when X-rays are incident with a very small grazing angle, the angle between the surface of the mirror and the incident rays, when it is very small, so less than a degree or so. In that case, in the grazing incidence case, the X-rays can be reflected through the principle of total external reflection. That is how you make X-ray reflections. It is also possible. It is also possible to reflect X-rays in the near normal incident, but that requires multiple layers of deposition of elements. So the lighter and heavier elements, alternate layers of the deposition. In that case, that works like a crystal structure, and through the reflection process, it can also reflect X-rays, and that is how I think the NewStar mission is specifically in the hard X-rays, and it has multi-layer coating, and utilizes this multi-layer coating, multi-layer thing to reflect X-rays to make the telescope. Any other question?
Can you suggest some reference?
Good. Okay. Here are the references. So you are just reading the first book, Exploring the X-ray Universe. It's a very nice book, and it's a very much readable. And master's level or even earlier. This is a very nice read. And Phil Charles is one of the very well-known scientists. So actually also is one of our regular visitors, and we also collaborate. But this book is really nice for a first read. It gives the title suggests Exploring the X-ray Universe. It actually talks about a lot of things in X-ray astronomy, different kind of sources, technology, etc. With a very recent things as well. So if you are really interested in X-ray astronomy, this should be the first book to read and know about the X-ray universe. Okay, then there is a book by Handbook of X-ray Astronomy. This is more technical book. I mean, it explains how X-rays are detected, how the X-ray telescopes work. Many other things which I taught, which I told you in the last two lectures. So those things are covered in much more detail there. The Handbook of X-ray Astronomy. This is also recently. Then actually, if you want to learn about the astrophysics, high energy astrophysics, the physics part of X-ray astronomy, then you can read Astrophysics by Malcolm S. Longyear. This is a thick book and it talks about a lot of physics, starting from stellar physics relevant for high energy astrophysics, then all kinds of high energy astrophysics processes of very different kind of sources, like binaries, whatever we can think of, which can be radiation, astrophysical jets, etc. So this at a PhD level or even MSc level, if you are really working on this, then that's a very good. And these three books are, I think, of course, there are websites where you can familiarize. For example, the NASA website, NASA's high energy website, ISSAA, that lists all the X-ray missions, X-ray satellites, the past ones, the current ones. And if you are interested in research in X-ray astronomy, you can visit the website. That will be useful because not only it lists the various satellites, it gives access to the data already acquired with this telescope. It also gives access to the software which you need to software data. It also tells gives you the documents which you will need to read to understand the instrument as well as the data analysis software. And for IUCAA, for associate, this is the website.
Sir?
Yeah.
So what exactly are ultraluminous X-ray sources and the cause?
Okay. So the ultraluminous X-ray sources are off-nuclear point X-ray sources in external galaxies, particularly in nearby galaxies. So if you image nearby galaxies and X-rays, if there is an alien, then the center of the galaxy will be placed, right? You'll see that. But in addition to that, you will see several point sources. And generally, these point sources are expected to be X-ray binaries. X-ray binaries, when we say the neutron stars are black holes, stellar mass neutron stars are black holes, which will be emitting these X-rays. And the luminosity of these sources will be lower than certain limit because the maximum luminosity, so-called the Eddington luminosity. Have you come across the Eddington luminosity? No. So the Eddington luminosity is the maximum luminosity a source can emit. If it is emitting more than the Eddington luminosity, then these photons will interact with the surrounding material and through the quantum scattering, they will throw out the source. They will disrupt if the luminosity exceeds the Eddington luminosity. So therefore, the luminosity should be lower than the Eddington luminosity. And that luminosity depends on the mass of the complex. And when we are saying stellar mass black hole, so like something like 10 solar mass or even 20 solar mass or even 30, 40 solar mass stellar, then we have a maximum luminosity possible for the stellar mass. But this ultra-luminous X-ray sources are, as I said, these are off-nuclear X-ray sources in nearby galaxies. But their luminosity exceeds the maximum possible luminosity for a stellar mass accreting black hole. Those are the ultra-luminous X-ray sources. And these were detected with Chandra and Newton soon after their launch, 1999, 2000, etc. It's become very much interesting because if the stellar mass objects cannot explain that these could be the intermediate mass black holes, somewhere between the supermassive black holes with million solar mass black hole and the stellar mass black hole, 10 solar mass black holes. So some of these could be, but we don't know. But surprisingly, sometime back, there was a very interesting discovery from these sources. Some of these sources were the pulse X-rays, very similar to the pulsars, which are neutron stars. I mean, 1.4, 1.5 solar mass kind of pulse. But then, how come they have such large luminosity? That's still a question. And whether all the alternative sources are pulsars, or some of them are really the intermediate mass black hole, maybe 200, 500 solar mass black hole. That would be nice. All right, so I think I'll stop.